Today we are going to record our lesson number 2 for chapter 3. It's entitled Heat and Conservation of Energy Principle. Our quotation, it says, heat energy of uniform temperature is the ultimate fate of all energy. The power of sunlight and coal, electric power, water power, winds and tides do the work of the world, and in the end all unite to hasten the merry molecular dance by Frederick Soddy. Let us try to see our MBCA boosters. It says, we have our text found in Psalms 103 verse 5, Lord, renew my energy when I feel tired and weak. So question, in what situations or experiences you feel tired and weak? And then write your personal prayer. Alright, let's try to enumerate our targets for this lesson. At the end of this lesson, we will be able to infer that heat transfer can be used to do work, and that work involves the release of heat, and state the first law of thermodynamics as the law of energy conservation applied to thermal systems. Okay, how does work relate to temperature? Place a handful of dry sand in a metal container that has a cover. Measure the temperature of the sand with a thermometer. Cover the can and shake it vigorously for a minute or two. Now, predict any change in the temperature of the sand. Was your prediction correct? We try this as part of the adventure. Let's try to answer the following questions. In your own words, how can heat transfer be used to do work? And that work involves the release of heat. What is your own idea of the first law of thermodynamics as the law of energy conservation applied to thermal systems? Okay, here, chat with the expert. Let us try to dig down our lesson. The thermal energy of a system can change in many ways. The engine of an idling car becomes warm because too much of the energy released when the gasoline burns in the engine are converted to thermal energy, like what you experience in working your palms when you rub your hands together vigorously. The what we have done in lesson 1 in Venture. They become warm because work done by the muscles in your arms is converted to thermal energy caused by friction as your hands rub together. In its natural condition, heat always flows from object of a higher temperature going to the object of lower temperature. During this process, the object with a higher temperature loses heat while the object with lower temperature gains heat. The amount of heat lost is always equal to the amount of heat gained. In other words, heat energy is conserved. It is neither created nor destroyed. If this energy conservation is applied to thermal systems or systems involving changes in temperature, then it is called the first law of thermodynamics. This can be stated as the heat added to a system equals an increase in the internal energy of a system plus the external work done by the system. In all thermodynamic processes that were discussed previously, energy has been conserved. To understand the overall change in the system's internal energy, the heat energy that was transferred into or from the system must be accounted for, and the amount of work done must be determined. From this law, when the heat is added to a system, the system does one or both of the following things. Okay, let's enumerate this. Number 1, the heat may be used to increase the internal energy of the system. Second, the heat may be used to perform external work done by the system. And for our mathematical formula for the first law is the change in Q is equal to the change in U plus W. Okay, so where our change in Q is the heat transferred into or from the system, and the change in U is the change in the internal energy, and W is the external work done by the system. From the above equation, it can also be analyzed that the system's internal energy can be changed by adding or removing heat or doing work or both, mathematically expressed as Okay, we can derive another formula, and that is the change in U is equal to Q minus W. Alright, here we have our table that summarizes the heat and work for a given system. Okay, for our table, we have signs of heat and work of a given system. So, if our change in Q, remember the change in Q is the heat transferred. Okay, energy is added to the system as heat. If the change in Q is greater than 0, so the energy added to the system as heat. Our internal energy increases if W is equal to 0. Okay, again, what's W? It's the external work done by the system. The change in Q is lesser than 0. Energy is removed from the system as heat. The internal energy decreases if W is equal to 0. So, the change in Q is equal to 0. No transfer of energy as heat. No internal energy change if W is equal to 0. Okay? So, W is greater than 0. Work done by system or the expansion of gas. Internal energy decreases if the change in Q is equal to 0. W is lesser than or is equal to 0. The work done on system is compression of gas. Internal energy increases if the change in Q is equal to 0. Okay, W is equal to 0. No work is done. No internal energy change if the change in Q is equal to 0. All right.